We really come to models like this.
No, I meant.
Yeah.
Hello everyone, I am LuaJIT and Stefan. We are coming from RTMK company from computer-based systems, and we are here to present you our work on LuaJIT for AArch64 and MIPS64 platforms, which was sponsored by Cisco. So I suppose many of you are familiar with LuaJIT as a JIT compiler for the Lua programming language. And in its latest release version of 2.0.4, it supports can run on many platforms, but most of them are 32-bit platforms. There's, among others, support for MIPS and AArch62, but it is most noticeable that support for MIPS64 and AArch64 is missing. And basically, that was our task to add support to make LuaJIT runnable on these platforms. So we started with the MIPS64 interpreter. That's the first thing that we developed, and continued with ARM64 JIT because ARM64 interpreter was already available. So ARM64 JIT we developed in collaboration with colleagues from the Naro company. And these changes are now available from a few months ago on the LuaJIT development branch on GitHub. Now from a few days ago, we finished work on MIPS64 hardload JIT, and we submitted actually changes to the maintainer for review and uploading. So this is like a little announcement. And we are still working on MIPS64 softload JIT. So a little bit about changes between main two versions, 2.04 and 2.1. So the current release version supports only 32-bit GC references, which is suboptimal for many of 64-bit architectures. So this problem is solved introduced the GC64 mode, which enables using pointers up to 47 bits for pointers, meaning that you can now address allocate memory from address space that is up to 47 bits, address lower 47 bits instead of only 32. So at first, this GC64 mode is implemented only for interpreter mode of the X64 and ARM64 platforms. And not long after that, first JIT port of that mode was available, and that was for the X64 platforms. And basically, we use that as a reference in our work for other two. So in a little bit about the differences, GC64 meaning before GC64 was introduced, all the Lua JIT objects, which are 64 bits long, were represented with 32 bits for type and 32 bits for pointers. Why is that? Well, as you know, Lua is dynamic type language, and there needs to be a way to distinguish these types. And in LuaJIT, for that purpose, is used NAND tagging. As you know, there is a IEEE standard for representing floating point numbers, and in that standard, it's defined as there is some range of values that are defined as not numbers, and some of the values from this range are smartly used in LuaJIT for tagging the pointer, meaning setting the type of the pointer to the LuaJIT object. And as I said, in earlier version there were 32 bits reserved for type. Of course, there was example for light user data on 64-bit platforms where the pointer are extended to be possible to 47 bits long. And of course, there is always a case where LuaJIT is a number, then you will use 64 bits to represent that alphabet. What the new GC64 mode introduced is that now all the pointers can have are 47-bit long, and all the other 17 out of the other 17 bits, there are 4 that are used for tagging, for setting the type of the pointer, which is basically enough because LuaJIT uses up to 16 different types of values. And the other 13, I mean the highest 13 bits, are all set to 1, and it's kept that way in order to keep the recognizing of the not number values. So this is basically it for that. And now we'll see what main changes were for this 64 mode. So basically, in most part of code, you have the operations, 3 basic type of operations for handling t values. You often need to either extract the pointer or check the type of the pointer, or extract the or set the type of the pointer. And here we can see how these basic operations are handled through the targets or instructions. For pointer extractions, there is a defined constant with a lower 47-bit set, in which is used to counter that in end instruction for basically extracting just the pointer value. For pointer tagging, basically reverse process, we have we put in register a certain constant that defines that type, and then use it in the next instruction for addition. This register is now used as an operand, which is a bit in the same instruction shifted to the left for 47 places to place the type values, type value bits on the proper location, and keeping the other 47 bits on the original register, which holds the pointers. And for type checking, you only need to, of course, isolate higher 17 bits, and that's done by the shift right instruction, and after that comparing with a certain constant in order to determine if that's the pointer or the desired type. Something similar here is done with MIPS64 instructions. These instructions are from release 2 instruction sets, and it is really usable because for these operations we can use a lot smaller number, 1 or even at most 2 instructions for these operations. So for extraction we have a special MIPS extract instruction. For pointer tagging also there is special insert instruction. And type checking is more or less done in the same way as in MIPS, by shifting right value for the value 47 bits to isolate the pointer and then comparing. So basically, if someone tries to port LuaJIT to any new platforms, he needs to just take care to implement these 3 basic operations, I would say, in the most efficient way, with a little less, as less instructions as possible.
Please.
Okay, so now I will go a little bit into source code, and I would explain what someone might need to do if they wanted to port LuaJIT to another architecture. And this is all with an assumption that there is already an interpreter implemented. So you have an interpreter and you want to implement JIT. So the first thing, well, not the first, one of the things that you need to do is to implement missing pieces in the interpreter, because when there are some pieces in the interpreter that are only usable if you have JIT. Those things are like entrance and exit from JIT code, detection of hot code that needs to be JITted and stuff like that. You need to implement instructions for your architecture and define what registers it uses and stuff like that. You want to implement different emitters for instructions. So there are different types of instructions that use 3 registers, instructions that use 2 registers and constant. So you want to implement all those emitters. There is an IR to machine code transformation. So LuaJIT emits a special IR for Lua code, and that IR needs to be transformed to machine code for your architecture. And this is where you want to do that. And you also want to implement the disassembler for your architecture. It's just as it sounds, a disassembler for your architecture. So the first thing is the interpreter. As I said, hot loop detection, exits from JIT code, entrances to JIT code, trace stitching, etc. Those are all the things that you need to implement. This is a function that handles exits from JIT. So when something happens in JITted code, so it finishes or it fails, you want to go back to interpreter. And mostly every example that you are going to write is going to go through this function. So you want to get this function implemented properly in the very beginning of your code. One of the things that you want to do in this function is, first of all, you want to save the state of the JIT. You want to save all the registers that you use and put them on the stack. So those 3 dots are actually a missing code. That code basically just says store all of the registers, all of the general purpose, all the registers to the stack. You also want to make sure that you extract exit number and parent properly. Those are mostly different for every architecture. So the target file, that is a file with a lot of defines and macros. You want to define all of the instructions, all those instructions that you're going to use. So it's just an instruction with an encoding. You can probably find that in reference manual for our architecture. You want to encode instruction fields. So you want different destination registers on one encoding, source registers on different encodings. So those are instruction field encodings. You also want to define registers, how many registers your architecture has. Does it have a floating point unit? How many registers floating point unit has? How many registers are used for function calls, etc. This is an instruction emitter. So we have 2 functions here. These are the simple ones. The first function emits an instruction with 3 register operands, so D and M. You pass assembler state, one instruction and 3 registers to it, and it just merges those all of that information and puts it into machine code pointer. The branch that it emits a PC relative branch or PC relative jump instruction. It just needs to get the current PC, subtracted from the target pointer and encode it. If you're not familiar, this is not going to make any sense to you, but it's not that hard. This is a little bit more complex emitter. It emits a load from our store to a pointer. So you pass it a pointer and a register, and you want the information in that register to be the information that the pointer points to. So first you have to. So this is for AArch64 architecture, and ARM has some specific instructions. So it has a PC relative load. So you first want to try ask, can I do a PC relative load? If I can, then do a PC relative load. Else I want to try something different, like GL relative load. The GL is global state for LuaJIT. If you can't do that, then you just allocate a register for that pointer and load it slowly, and then after that load from that register. That's the slow path you apply. The ER assembler. This IR assembler has a function for every LuaJIT IR instruction. The ones present here are minimum and maximum IR instructions. So they are implemented in one function, but they are defined as macros. So when LuaJIT gets a minimum IR, it's going to call a min ASM min function, and well, there is a different path if you're doing floating point minimum maximum, and if you're doing integer minimum maximum, you want to do different things. You want to use different registers. So this example here shows the integer minimum maximum. So what you want to do, a minimum maximum is a 3-operand instruction. So it has the result, the one value and the other value, the left and the right, and you want to know which one is minimum. So you allocate the register for destination, and all these functions that start with RA are register allocator functions. So you want to allocate destination register, you allocate left, you allocate right register, and you emit the two instructions, compare and conditional select. So you want to compare values first, and then you want to conditionally select. If one is higher, then, or if left is higher, then you select left, and if it's a maximum, and if it's a minimum, vice versa. And as you can see here, the conditional select is emitted first and then compare. That's because LuaJIT emits the code backwards. So if you take a look here, you can see that the pointer, the machine code is decremented. So it's generated backwards. So don't let this confuse you. The other thing you want to pay attention to are optimizations. There are probably an architecture-specific optimizations that you can do. For AArch64, these are some of the optimizations that you implemented. So when you write in Lua A plus B times C, you can actually get that to be just one instruction. So, and Lua is a dynamically typed language with dynamically typed interpreted language, and all that is just one instruction. That is pretty impressive to me, because usually in interpreted languages you get a lot of instructions for some expression like that. Also, there are interesting optimizations concerning loading concepts. You want to look at that, and you probably want to look into popular compilers like GCC and LuaJIT to find ideas for these optimizations. So now for the changes on MIPS64 part. As I already mentioned, we did interpreter port and JIT port as well. As for today, we will not give some more details about interpreter port, but just to mention that all the changes were related to earlier mentioned key value tagging operations. And JIT part changes are pretty much similar as the changes that are done on AArch64 board. The thing that we are going to do, MIPS64 soft load, will need a little bit specific change than earlier to board because in current state LuaJIT doesn't support any 64-bit soft load architecture. So in order to enable that, we need to make a little changes in split pass, precise disable splitting 64-bit IRs into two 32-bit IRs. And after that, continue the normal work that we planned, handle floating point arithmetic properly, meaning to make sure that we don't generate any floating point instructions and call functions in proper manner. So that's about it. And here you can see benefits of this work. On these slides are represented changes, result tests that are run on ARM64 platforms. And these bars, the red bar represents how many times LuaJIT was faster compared to Lua 5.1 interpreter. And blue bars are just here to show the difference between LuaJIT's interpreter and LuaJIT's when it's JIT compiled in native mode. So that's about it from us. If you have any questions? Yeah.
You said that in the 64-bit soft float, you're going to divide it into 32 and then call it. Are you going to call 32-bit soft float?
Please repeat the question.
So yeah, the question is if we're in soft float, we're going to divide 64-bit instructions. The answer is that in the current state of code, it's already been doing for soft floats. So 64-bit instructions are divided into 32-bit instructions. We wanted to disable that because it's not longer necessary.
Okay.
Yes. Is there any specific about FFI module and floating LuaJIT and other architecture?
Well, there are specifics in the interpreter, and in JIT there are a few things that you have to take care of, but nothing special. But well, in interpreter now there are a lot of things that you have to take care of because you have to implement a calling convention for that architecture. Which registers you want to use, how do you want to how do you use stack, how do you pass values and things like that. And it can get complex. I guess that's it. Thank you.